Yeah. Right. See, okay. I am in physics department. Today I'll be giving a very short intro on introduction to cosmology, basically how cosmology has evolved as a science and as a subject over the years, and what we essentially mean when we say that we are studying cosmology. So cosmology is basically study of the universe or the world. It comes from Greek. The word root comes from Greek. Cosmos, that means world, and Iowa, sorry, problem. That is a study of. So essentially, it just means a study of the universe. Now, studying the universe, that's the universe is quite big. But So any attempt to study the universe will lead us to estimate the universe as a very an ideal smooth universe. And by ideal smooth universe, here I mean what I have is that the texture or the structure formation in the universe is quite different at very large scales, right? So for different scales, we have different type of structures or different densities. So we need to estimate a very smooth universe at very large scales. Now, the other two types of there are types of cosmology as physical cosmology, religious or mythological cosmology, and philosophical cosmology. We'll only be discussing cosmology, touch upon for very obvious reasons. And so, moving further. Now, to study something, we need to observe, we need to take observations, right? So, for any experiment that we perform, we need some way, means to observe the system as well. So, how do we observe the universe, right? So, the ways that we can observe the universe is using visible light. There are other bands in the EM spectrum as well that which help us, that is microwaves, radio waves, infrared, X-rays. All these help us to observe the universe. And then there's also gravitational waves, which is an upcoming, not really upcoming, it is actually there. So it is another means of observing the universe at a much deeper scale. Uh, by scale here, I mean at a much later time than we have been able to observe with, say, infrared or X-rays. Moving on. So, yeah, one of the cornerstones of cosmology is the cosmological principle. And now, what do I mean by the cosmological principle? Alright. So, the cosmological principle formally is stated as viewed on a sufficiently large scale, the properties of the universe are seen for all observers. Now, what does this statement essentially want to say? Any any guesses on what the statement is trying to say or trying to put? No, no one wants to venture a guess. All right. So essentially, this cosmological principle is stating that on a large scale, the universe looks all the same no matter where you are. So humans have been very self-centered, right? Throughout the time, humans have been very self-centered. Any natural phenomena that is occurring, say, for example, it's raining, lightning strikes. Humans have this idea that everything is centered around them, and they form the idea that yeah, rain gods are angry. That is why it is raining so much, and all that. So humans have a very self-centered opinion about their special position in the universe, and it has also been seen throughout the time that saying that the humans were not ready to accept that we are not occupying a major part of the history, that we are not occupying a special position in the universe. That is, we are not at the center of the universe. So yeah, so it's very simple about the place we occupy in the universe is always special. Universe will look exactly the same no matter where we are. Alright. And it is a property of the global universe, that is universe at a very large scale. So by scale, large scale, what do I mean by large scale? A few kilometers, can just a simple yes or no. A few kilometers, a few megaparsecs, a few light years, a few million light years. Yeah. So the scale that we are talking about is a few billion light years. And this cosmological principle breaks down at very small scales. That is scales less than anything which is say 100 million light years. All right. So unless we have a few 100 million light years, the cosmological principle won't stand. All right. So what is the scale of cosmology? Basic unit that we consider is galaxy. Then comes galaxy clusters and superclusters or dark matter, GLOs. And then we have the observable universe. So the basic unit is galaxy. Its size is measured in kiloparsecs. It's a few order of 10 to 100 kiloparsecs. Then a galaxy cluster ranging over a few megaparsecs. Then superclusters ranging over a few hundred megaparsecs. And then the observable universe. Dark matter halos range over a few like million light years. All right. So the now the Hubble volume that I'm going to talk about. Now, what exactly is Hubble volume? It is said that Hubble radius is equal to c by h naught. All right, and it is equal to about 14.4 billion radians. Does this number sound familiar? 14.4 billion. Yeah, I just said that. It is the size of the observable universe, Hubble radius, but the number 14.4 billion, right? 14.4 billion. Does it sound familiar? If you change the units to years, 14.4 billion years, age of the universe. Age of the universe. Yeah. So Hubble volume is basically the size of the observable universe. And it states that any part of the universe at the max that we can observe is basically that as big as a Hubble radius. It's actually in uh, factor of Hubble radius. Some additional factor is there, right? But yeah, so essentially it states that time, age of the universe times the speed of light. That is the maximum that we can observe. All right. And as we know, universe is, of course, expanding faster than this. All right. So it's much bigger than the observable universe that we know. Now, right. Few large scale, now a few properties of the universe, right? And cosmological principle that is, as I just said, that the universe, no matter where we are, will look exactly the same. And why is that so? Because the universe has large scale homogeneity and isotropy. Now, what does these two things mean? All right, homogeneous, that universe looks same at each point, right? So no matter where we are, the distribution of matter around us is pretty much same on a large scale, right? So the scale that we are talking about, a few million light years, few hundreds of millions of light years, right? So this universe looks same at each point, and isotope universe looks the same in all directions. So when you are observing across the line of sight, the distribution is pretty much same across every line of sight that you see. So no matter my line of sight is like this, the universe will look exactly the same in both directions. Alright. So any guesses about how a model of the universe, a pseudo model of the universe that is both homogeneous and isotropic? You just saw these two diagrams, right? Of a homogeneous body and isotropic body. So say you are sitting at the center of this body. No matter where you look, the this sphere looks the same to you because the matter is distributed that way. And there's a homogeneous body. No matter where you are, the distribution looks exactly the same. So any ideas about how it will look if it's both homogeneous and isotropic? Sorry, universe is homogeneous and isotropic at points. It is a property of, especially when it has a cheat very large scale. So yeah, right. So all right, but if there's a spherical symmetry, the universe would be homogeneous. You see this, right? Yeah, this figure. So if it is spherically symmetric, right? However, when it is spherically symmetric, the distribution will matter according to the RT. So it won't be homogeneous anyways. Like at different points, the distribution will look depending upon the R theta pi coordinates that like a sphere. Yeah, it's an infinite sphere, right? But then you're saying that once it is spherically symmetric, you're saying that universe has a center, which we just discussed that it does not, because every point looks exactly the same. It's a very easy answer. Once I tell you the answer, you will be like, what was this? You needed to ask this. Yes, yes. This. What other distributions do you know? But if there's a very large sphere, then there's an average or sentence or yeah, but see, spherical symmetry will wait, when you say there's a spherical symmetry, right, that means there's a distribution, the density of the universe changing by some parameters when you change some parameters, right? It might be theta, is the angle and the R, right? So increasing this density might increase and fall. That is not happening in our case. Right? I did not know you guys, but I wanted you to come to the same conclusion. Any more answers? You want to try and guess? Just say anything random. Guys, please come in. The universe does not have any bone edge. I love. This is a very interesting topic. Because this is universe. Anything random that you want to answer to this question? Like the same vector space. Sorry? Same vector space, even. What do you mean by vector stays the same? What I mean by this imagine infinite space. Yeah. After directing in every direction, still directing every direction, regardless of the current of the coordinates. It's not a static coordinate. So I'm standing here. It's a sphere of vectors. I'm imagining the sphere, right? And each point of sphere is subtends, say, a vector to the center, right? So it's from the center to the sphere, each point of this sphere. Now, if I move that point to the side, won't the distribution of the vectors here become, like an offset from the center? Oh, good. All right. So, okay, fine. Let's not take up much more of the time. So the answer is not this, is this. It will probably look something like this, a completely random distribution. I will give you the answer. Say random. Anyways, yeah, so it is something completely random. Of course, over very large scales, right? So the scale that here we are talking about, the scale of the for the newcomers, is the few million light years, and we're talking about the homogeneity and isotropy over those distances, right? So yeah, now it will look completely something like that. Now, yeah. So this is a pseudo model of the universe. Might look something like this. Alright, now what evidence do we have for that large scale homogeneity and isotope? How do we know that the universe is in fact on such large scales homogeneous and isotope? So the evidence that we have is galaxy counts, determination of peculiar velocity field of the universe. What are these? So this one is Hubble ultra deep. This is in which taking the sky. And this is by JWST. See, alright. And yeah. So what do these images represent? Alright. So coming to Hubble. So these images are of the part of the sky which is as big as a grain of sand held at an arm's distance. All right. So you can imagine how small a grain of sand is. All right. You hold it at an arm's distance, and you can't even see that part of. All right. That grain of sand. All right. And the Hubble telescope focused on that part of the sky and it took around days of exposure data. All right. I don't remember. It's about some 50, 60 hours of exposure data, focusing on that small part of this. And each dot that you can see, each bright dot that you see there, all right, it's a galaxy in itself. All right. So you can imagine what at such in such a small part of the sky, there are thousands, not millions of the galaxies. And this is that we can see. Right. And there's an unknowing universe beyond, even beyond the observable universe. Right. Same like the JWST. I think that is the same part of the cell. But yeah, same grain of sand, elder than arms distance. Alright. And this determination of the particular velocity. So velocity field here refers to the velocity by these galaxies or galaxy clusters that they have in the universe. So we can determine them by a few methods. We will talk later. Discuss here. However, so yeah, these are the galaxy count service. Another very interesting evidence and one of the more prominent that we, of course, refer to is the uniformity of temperature of CMDR. Now, what is CMDR? Does anyone know? Cosmology. Yeah, so the cosmic microwave background radiation, right? And so this is the graph that we do. When we plot each point in this sky, we take data and we try to measure the temperature of the medium. Right. And this is around 2.7. Right. So around 2.7. And you can say that the universe temperature of the universe at that not state. Okay. So now these are two plots that we these are quite important. Right. And can anyone okay. Yeah, can anyone identify what structure you're seeing in this. Right. Now, let me tell you a little bit about this plot. It's of the temperature that we're getting from the cosmic sorry, microwave background radiation that seen here on Earth. And the blue ones, extreme of the data. All right. And the red ones, the extreme. And those two extremes differ by an order of only 10 to the power minus 5 Kelvin. Alright, so it is 2.7 Kelvin plus 10 to the power plus minus 10 to the power minus 5. And there's a structure that we observe. Does anyone know what structure that is? Any guesses? Okay. Yeah. Can you please explain the plot again? No, or what CMDR is? Okay, the question I'm trying to ask is from Earth, all the data for CMPR that we're collecting, right? It is represented by this one, right? And if we remove that structure, it is somewhat uniform like that, right? It has even a lesser error bar, right? So yeah, And this difference is attained by minus 5 Kelvin. And we are observing the structure. What is the most prominent structure that we will see? We are looking around from Earth. What structure? Structure as in yeah, lucid dreaming galaxy. Yeah. So right. So we observe galaxy in the night sky. It is one of the most prominent and there is millions of stars in the Milky Way galaxy. Right. And we are observing this. This dark structure is contained within an error bar of 10 to the power minus 5. All right. Degree Kelvin. That means it is so uniform that a slight, very slight change in temperature is being caused by a whole galaxy. It is that uniform, this CMP. All right, and so we remove, we can remove. This is the map of the CMPR of the universe that we're getting there at. All right, and so this CMPR is very uniform, and that gives us an idea of the how homogeneous and isotope. Because you can't really make out anything on this map. It's completely random. There's no distribution. So we can say that it is homogeneous and isotopic at very large scale. Moving on, another one is the isotropy of the X-ray background radiation. So this is a picture taken by Rozak, and it is a picture of the moon. It just collects all these the X-ray background radiation that we're getting. And I just included it because it adds to the like how how uniform the X-ray background is apart from the AC moon, right? So this is X-ray reflected off moon, and you can see it's completely dark then, right? That is meaning there's no X-ray coming off the dark side of moon. The neighboring part, okay, you can see a lot of side. Moving on, we discussed a little bit of the history of cosmology, how it has evolved over time. Actually, I'll just be discussing a little bit about the most interesting experiments that I found, which I find. See. So, right, this is one of the one of the experiments which was performed in 1670, 200 years ago. Right. No, 300, 400 years ago. All right. And what Cassini tried to do was he wanted to give an estimate the dimension of the solar system. All right. How big is our solar system? Because back then we did not have any idea of the dimensions between uh, the length scales between Earth and other planets between Sun. Right? We did have a little bit of idea, but he wanted to calculate how far is Mars. So what he did was he calculated this distance using Martian parallax. Now, what is parallax? You guys are doing your first year physics lab. They must have taught you a little bit about parallax or parallax error, right? What is parallax? Any one of you? Yeah. Right. So you can observe it. How can you observe it right now? Just hold your thumb like this, close one eye, and see your thumb will shift. So that is parallax. And you can observe it at the cosmological scale as well. Right. So what he did was he asked one of his friends in Venezuela, who was in Paris. He asked him to measure uh, the location of the Mars in the sky. All right. So what he did was he was in Paris. He asked his friend, measure the smith position of the Mars using the background of the stars. Cassini was lucky that the background of the stars is pretty much static at shorter time scales. Right. So he was able to get a good position of Mars. Now what he found was that Mars changed its positions due to change in location. So Mars is somewhere there. All right, there's a background of the star. Now, how do I know that my thumb is moving? Because I can see the background behind, right? So from different locations on Earth, he saw that Mars shifted its position. Right. And by using that parallax error, he could estimate the distance between Earth and Mars. And he gave that the distance that he got to was around 140 million kilometers. All right. And which has an error less than 10%. It's around 7 or 8% error. Right. From today's known and accepted distance, which is around 150 kilometers. Right. So this was the experiment that another very interesting experiment that I found. Sorry for the image. All right, I'll explain what this experiment is about. So this experiment is actually telling us about the finite speed of light. So until 1676 and a little bit after, people always believe that speed of light is basically infinite. All right, because at any distance that you can fathom here on Earth, right? It's you did not have also have atomic clocks back then, so you could not measure the very short time scales. So they estimated that yeah, it is infinite. Yeah. Only Roman, right? He was not convinced, right? So what he was an astronomer, and what he was doing one day that he was taking actually he was trying to calculate the orbital time period of Io, one of the Jupiter's moons. So what he did was, as Io went behind the Jupiter, got it? All right, and Io has an orbital time period of a few days. All right. So over the year and over a course of few years, right, so he observed the orbital time period of Io. All right. And what he found was over the course of year, as the distance between Earth and Jupiter changed, the time period of Io's orbital around Jupiter also was different to him. But why was that? He assumed that, of course, Io has a pretty steady orbit around Jupiter. It has been millions of years, billions, no, billions of years since Io went around Jupiter. And it was pretty steady. So why is there such a big time difference? And yes, also saw was that over the course of year, because he roughly knew about the orbits of Jupiter and so he could estimate that when Earth and Jupiter were closer, right, the time period of orbital Io's orbit around Jupiter, like when it was going back behind Jupiter and when it was coming again in front of the Jupiter. So basically the eclipse of Io behind Jupiter. So that time period was shorter than some 10 minutes, like 10 minutes or something. And then there was a big difference when Earth and Jupiter were like that, and when they were far distant from each other. That time period was even great. Right. So it did not by a few minutes, but it was enough to for him, and it was enough for him to and also periodic enough to suggest that light does have finite speed, and the speed he gained was also not very accurate. It was off by a huge margin, but he did justify it why light has finite speed. Right. So now a little bit about Newtonian cosmology. Right, Newton, favorite scientist. So yeah. So what he assumed was a very static universe made up of stars and everything. But their stars are uniformly distributed throughout the space, which we know is not true. There's quite a bit of distance between galaxies. Okay, but also it is a very unstable configuration. Okay, and you can justify why it is so unstable due to these two Newton's own law, Newtonian gravity and lucidity. Okay. Now, why do you think it is such an unstable model of the universe? Like any guesses? So yeah. Yeah, even a short, even a very small disturbance, perturbation in that static universe. Huh? Yeah. Yeah. So even a very short disturbance in that universe will immediately make it collapse under its own gravity. Because you might have seen that magnets put together nearby, and as soon as you put another magnet or you displace one magnet, they all clump together. You might have seen things. So yeah, all that would collapse even if there is a very short or very small perturbation in that. Correct. Moving on. Yeah. So now we come on to the original Big Bang, and it says that the universe expands from an initial state of very high density and temperature. All right. And there's another model of the universe that is getting forward. Does not have any evidence as such. However, one of it is the cyclic model that universe is always expanding and contracting in cycles. All right. So this is what urban treatment demands. This is what the cyclic ones. Back of big crunch, the radiation dominates, matter dominates, dark energy dominates. It's another contraction, and then a big crunch. All right. So moving on of our universe. So yeah, this is the energy density or the contribution of to the energy of the universe by different components. There is ordinary baryonic matter, the matter that we see in everyday life, the matter that forms us, the stars, the galaxies, that kind of baryonic matter. Then there's dark matter. It consists of and so there is dark energy. Right? So dark energy is a mysterious force that the universe to access. Okay. And it accounts for a large related. Alright, now I wanted to discuss a little the particle metric. This is how do this so yeah, dark energy. How did they find power? Right. So for dark energy, they did run a calculation, right? And they find that the universe would not be still be expanding. All right. We'll see what expansion is. All right. So universe would still not be expanding if it were not for mysterious energy. Right. It should have collapsed by now if there was only baryonic or dark matter we know because the rotation of the galaxies do not match with the mass that we can observe in the galaxy. Right. So this whole another topic. That's a whole another topic. And for dark matter, the expansion of the universe, we cannot account for it until we take into the dark energy into consideration. Yeah, so a little about expansion, right? So we'll see how expansion we take into consideration. So this is something called Minkowski space, alright, and this helps us to account for the expansion and curvature of the universe. You might have heard that we have a flat universe, nearly flat universe. So what do we mean by that? Alright, so Minkowski space, it's basically ds is equal to minus c dt square, c square dt square, plus dx square. Dx square here refers to the spatial, right? Okay, it might be going a little up the top. Alright, so yeah, this takes into account the time as a dimension as well, and of course the 3D space. Okay, just understand this. Okay, this is time. This is the spatial S. The DS basically depends on metric on the space. Yeah, metric of the universe as a four dimensional space. Alright, so then we have something called the FIR metric. This is helps us understand mathematically, of course, how the universe is expanding. Alright, so this is again time. This is the A square T. Sorry if the equations are a little blurry. A square t, this is the scale factor, and this k right here, 1 minus k square by r square upon capital R square. R square, capital R square is a scale distance, and the small k is the curvature of the universe. So positive, negative, or flat universe. Those all three have a value that is 0, +1, -1. Belong for that curvature of the universe. You don't understand it, it's not very important. Then we have a Friedman equation. This tells us about how the universe is a because it means that spatial coordinates are in the usual identifier. Okay, article. Yeah, in that you can take both Cartesian and that, but the calculations are a bit different. Okay, all right, for the spatial method. Here, FRW just takes spatial. Okay. Now, Friedman equation tells us about how universe is expanding. Right. Won't go over it. I might go over this one a little bit. So yeah, the Friedman equation here tells us about the A is the scale factor. Now, what is scale factor? Scale factor tells us about how the distances are increasing with time. Increasing or decreasing. Scale factor might uh, be decreasing with time as well. So it all depends. Scientists calculated the mathematics. Okay. So yeah. So the change in scale factor will tell us whether our universe is expanding or decreasing. And this is the equation. And this takes into account the density of the universe, this curvature term, A, C, A square T, right? And also theta. So from here we can say that yeah, universe is expanding because we cannot account simply by curvature or density. We have to take into account the charge energy as well. Right. So hope that answers your question. Also, we also take into account different components. This is radiation term. This is Hubble's constant, h square t. Hubble's constant varied with time. Right. This also is an estimate the change in scale factor. So we have radiation, we have matter, we have curvature, and we also have. Alright. Moving on, expansion of the universe. It's a key piece. So everything that we are observing in the universe, this root that comes from is mostly from expansion of the universe. And how do we, what is the physical evidence of expansion that we have? So the physical evidence of expansion that we have comes from the receding galaxies. Right. So how do we measure the velocity? How do we know that galaxies are going far away from us? So we measure the velocities of the galaxy via redshift. You might have heard of the term redshifting. These JWST images that come up. They are also mentioning something that there's an object at redshift 10 that we are observe. Right. Now, what is this redshift? Now, redshift accounts for how much expansion or expansion in the sense how much expansion has occurred from the time that the radiation was emitted from that galaxy and the time that it reaches us. Right. So the formula here is given by lambda observed. Right. So the lambda that we are observing present time. And we know the lambda, right? Because object in the uh, each object in the universe, we know that it emits a particular type of radiation, and we also know the wavelength for right. So we know the lambda at which star is emitting which kind of time. And yeah, so we just divide it by 100. That gives us a value for Z, that is redshift. And that also tells us because E is also equal to V by C. V is the speed of object moving away from us. So if we have redshift, we can tell how far, how quickly that object is away from us, which gives us an idea of how fast the expansion is happening. But what do you mean by the expansion of the universe? I talked about there's a scale factor involved, which helps us in scaling the distances between galaxies and everything. But what is the physical meaning of the expansion that is happening? Yeah, that we covered it. Yeah, distances between the galaxies are increasing. So does that mean the distance between me and the stars and between each and every one of you is also increasing with time? So that would mean that but speed of light is constant. So that means that I should be seeing less of you by as the time goes on because time to reach me, but that does not happen.
Fact Andromeda is getting closer to
Yeah.
Milky Way.
So if the distance between you and me should be increasing, distance between my should also be increasing. Right? That should take more time to reach you from you to me. But I don't see that. Nor do the scientists, because then they would have there would be some failure. So what do you mean by expansion of the hint? There's a hint that start with what it does not. Right. So start with small scales. It does not mean that distance between you and me is right. And why is that happening? But we know that distance between galaxies is because we observe it that galaxies are moving farther apart from us due to redshift. So why is that not observed at smaller scales? There must be something that is restricting the expansion at smaller scales. Okay? There must be something. Now, what is that? The idea is what is expansion? Two things going away from each other. So there must be something that is trying to bring us together. Huh? Gravity, yeah. The forces between two molecules at small scales. So they overpower expansion because expansion is not that strong. Alright. It is observable at large scales because at those large scales there's very less forces or there's too much vacuum to which counteracts those scale forces that are pulling objects towards one another. That is why we are observing expansion at larger scale. We are not seeing an expansion happening between Earth and Sun. There's too much gravity between them. However, we are observing expansion between a galaxy far apart from us. And we can, so an idea of how fast or, so, yeah, so how fast this expansion is working. We get an idea of this from Hubble's, right? So Hubble, what he did was he went ahead and for quite a few galaxies, he saw what the redshift is, right, and calculated the velocity. Now what he found was that the further apart the galaxies are, right, the faster they are moving away from us. All right. Does that make sense? Yeah. So, so Hubble's law states that objects in an expanding universe move away from each other the velocity that is proportionally related to their distance. So he went ahead, he calculated the redshift. So this is the plot that we have in the beginning, right? So he plotted the velocity versus the distance of the galaxy that he was looking at. And what he found was there's this relationship, there's a linear relationship, right? You guys are in your first year physics lab. Anything that comes out, just do a linear prediction. And that is what he did. Great. Just take a first year chemistry student. He plotted a linear relationship and he saw that this relationship is working. Alright, he can observe that they have a linear relationship and the farther away, the faster they are moving away from us. Why is that happening? He gave the relation as v equal to h naught r. Alright, r being the distance they are apart from us. And h is the Hubble's constant. Right. He gave the value a bit off from the presently known and accepted value, which is around 71 kilometer per second per megaparsec. Alright, so we can what we see is that for each megaparsec away object is it is moving by a speed of 70 kilometer per second. Alright, and that was Hubble's law. Now he also observed few blue shifted galaxies, that is they are coming towards us. Andromeda galaxy, one of the more prominent blue shifted galaxies. Alright, there's going to be a galactic merger in a few million or billion years. Right, probably we won't be alive in the solar system won't be there. So yeah, that is what we observe. But yeah, so, but he was not the first one to observe. There was an American astronomer, Westo Silver, as well. So he was the first one to measure all these redshifts. All right, and he found that the spiral nebula with both blue shifts and redshifts moving at speeds which are too much, like too fast to be gravitationally bound to gravity. Okay. So these speeds are very fast. They can't be accounted by just the gravitational forces about the galaxy. So he found that they were too fast, and but he did not appreciate the full significance of his observations back. Right, because he was like there must be some error, or I'm doing something wrong. Right, because this does not make sense. Why would they be moving with 70 kilometer per second? That is quite a large speed at such large scales. Okay, and thought that it must be something else, right? And he did not do that. Eventually, Hubble discovered redshift. Uh, he- yeah, so he confirmed that for nebula outside, uh, see, distances 8 parsecs away. He saw this speed, and he estimated that it must be due to expansion that this is happening. At such large scales, expansion is happening at dramatic speed. That is why these two galaxies are much. So that conclude all right. There's a bit more. All right. Sorry. Sorry for keeping you. Okay. Now, why do you think the night sky? Promise this is last question. Okay. Ah, let me start. If I wanted to give you a little bit of cover to this question. This question is called Olber's paradox. Alright, why is the night sky dark? We just saw that that grain at a hand's apart distance. The image that I showed you earlier, this is so these are thousands of galaxies which are contained in part of the sky which is only one grain of sand big, like at Mars distance. So there are thousands of galaxies. The sky must be endlessly littered with objects that are streaming out light since God knows when. So universe is infinite and endless. So we must be seeing something like this when we are looking at the night sky. So there is the observer, right? Or the observer's eye, this the eye. There's a whole universe of sky, and the night sky must be looking something like this. Endless stars. But why do we not see? Like the night sky littered all with stars glowing just like the day. Why do we not see that happening? Any? Due to redshift. Sorry? Due to redshift. Oh, okay. Sorry. Due to redshift. So, what do you mean by redshift? The light coming from the stars is redshifted. Redshifted beyond our capability. So there must be redshifted so much that we are not able to observe with human eyes. Something like that. Okay. Any other guesses? Well, that's one possible guess. That's the point of view. But I just showed you that before. The point of but then even within that point, there are tens of, if not tens of thousands of things contained within that. So that must be giving us some. Why is that? Because the universe is expanding to the distance. Okay. Yeah. Right. Dark matter. Dark matter, dark energy. So dark matter does not interfere with light. Right? You can't see it with any known EM spectrum that we have. Right? So you can put that away. Dark energy, we don't have, we don't know what dark energy is yet. It's completely a mystery to us. Right? So we cannot say that. That might be what the personal explanations. Anything else? One of the wrong and the first answers to this Olber's paradox, this was given by scientist Stephen Olber, and the answer that Olber himself considered was right, was that there's intervening matter within these galaxies. So surrounded by a galaxy. Right. But that is not right. Surrounding matter within. We know that there's vacuum between galaxies. There's quite a bit of empty space between galaxies. But they did not know that. But why do you think that surrounding matter that was not the strike down for that surrounding? There was another strike down. I will tell you about that as well. So why do you think that surrounding matter thing was cancelled? Yeah, okay, fine, matter scatters, but there must be an absorbance spectrum that we must see because it cannot scatter everything. The sky does not scatter. You do get it because any object that where it is, unless it is opaque, it won't. It will allow some light to pass, right? And if it is allowing some light to pass through, it will heat up. Alright. So that surrounding matter has been there since eons, and it has been allowing the light to pass through. It will heat up, and it should also glow. Right. Then once it heats up, it will also emit some radiation. So we should be seeing additional radiation, but that is not. So now we know that there is no additional matter. But back then it was one of the counterpoints to Olber's theory that there's surrounding matter, the universe or the galaxies. What else can you think of? Maybe because stars which are closer to us, they are like we see our sun. We like we can't able to see other star. Like does that there is something because of that we can't see the stars which are far behind. But we are able to observe galaxies and even though our stars are present. Some of these galaxies are so far that the light does not reach us. Okay, a good point. A kind of viewpoint that he was also making that universe is infinitely expanding, so the light has not reached us. Right. Okay. So fine. The answers, the resolutions to these Olber's paradox. So first one, light is absorbed by intervening matter. I just told you why that won't work. Right. Light has a finite speed. Universe has finite size and age. So this was originally proposed by Edgar Allan Poe. Right. So what he said was that light has not yet reached us because the observable universe has a finite age and size. That is why light has not been able to reach us from all those galaxies and matter. One of the more prominent reasons. Then there's redshift. It has redshifted so much that we are not able to observe. But that is the redshift just acts up as a darkening. It does not completely eliminate that. But the strongest counterpoint to why night sky is dark is that universe has too little energy. All right. So, yeah. Now, what is this? It was proposed by Edward Harrison. And what he said was that even if you take all of the matter in the observable universe, you convert it to energy, to radiation, E equal to mc square. You know the the formula to convert it to energy. So all of the mass of the universe was converted to energy, and if we averaged it over the surface that the sky that we see, it would not even lighten up the sky even a little bit. It will still be dark. So it's not enough. The universe does not have that much energy to light up the night sky for us. And this is also mathematically, I'll give you a mathematical sense. So, what the density of the universe, right? Density of the matter in the universe is about one hydrogen atom per meter cube volts. Alright, that is the density of the universe. There is one hydrogen atom for each meter cube of the universe. So the density is quite low. So there's not enough energy in universe to light up the night sky. Alright. So these are the resolutions to Colbert's paradox, and this also concludes my talk. Sorry for keeping you all here for so long. If you have any questions, I will take them. These are all the things that I referred to. Thank you. So if you have any questions, I will take them from the top. Do you want me to go back to the slide? People who know, okay, well,
There's a difference between cosmology and astronomy.
Alright. So cosmology is as we saw, it's study of the universe and the radiation. Astronomy is more like observing thing. Astronomy is a more general term which also encompasses astrophysics, astrobio, and astrochem. Alright. Okay. Yeah. So astronomy is a more general encompassing term